video, I will be covering a topic that causes confusion to many students, and that is the topic of logarithms. Now, in order to understand logarithms and also be able to manipulate them, you have to have a very solid knowledge about exponents. As we will see, logarithms and exponents are inverse functions, which we will explain in more detail. So before you continue this video, you can first check out part 1 of this series. It covers the laws of exponents and exponent manipulation, and then move on to the laws of logarithms. I think the main thing that confuses students is getting their head around what is a logarithm exactly. Some students might be able to use the rules and apply them, but not really understand fundamentally what a logarithm means. Now, before we get into that, I want to introduce the concept of inverse operations. And this is something you're definitely familiar with. So for example, the inverse operation of addition is subtraction. The inverse operation of multiplication is division. So all these mathematical operations have an inverse, a way to reverse the thing that we just did. And that's the same with exponents and logarithms. A logarithm is the inverse operation to the exponent. So what do I mean by that? So if I say that 3 to the power of 2 is equal to 9, so here we're using the operation of exponent base 3, so our 3 is the base here. So we're saying 3 to the power of 2 gives us 9. This is equivalent to saying that the logarithm base 3 of 9 is equal to 2. So here, what we're interested in is the result. We're saying if we take 3, we put the power of 2, then we're going to get 9. However, here, what we're interested in is the power. We're saying the power of 3 that gives us 9 is equal to 2. If we say 2 to the power of 4 is equal to 16, if we write this in logarithm terms, then the logarithm base 2 that gives us 16 is equal to 4. So I want you to think of the word logarithm as the word power. What is the power that if we put on 2 would give us 16? Another way to think about it is to ask how big is 16 in powers of 2? So the logarithm is really about how big is a number in terms of powers of a certain base. So it's a way to assess the order of magnitude of a number. And this becomes very obvious when we're looking at logarithms base 10. So we know that 10 to the power of 2 is equal to 100. We know that 10 to the power of 3 is equal to 1,000. And that 10 to the power of 4 is equal to 10,000. Now in logarithm notation, we say log base 10, and notice here how I'm not actually going to write 10 at the bottom. 10 is the most basic base, and that is simply because we have 10 fingers and that's the base that we count with. So it gets its own special notation without having to write any number here. So whenever you just see the word log, it means log base 10 by default. Now, what is log of 100? So what are we asking here? We're saying, what is the power base 10 that gives us 100? And the answer is 2. Now, what is the power base 10 that gives us 1,000? That is 3. What is the power base 10 that gives us 10,000? That is 4. Or in other words, how big is 100 in terms of powers of 10? The order or the magnitude is 2. It's 10 to the power of 2. Similarly, how big is 1,000 in terms of powers of 10? It's of order 3 or power 3. And so on. A trick I like to tell my students whenever you see a logarithm notation is to start from the base and follow the arrows anti-clockwise. So you start from the base, and so you say, okay, 3, and then you follow the arrows to the power of 2 is equal to 9. Similarly, start from the base, 2, follow the arrows, and you get 2 to the power of 4 is equal to 16. Here you can do the same thing. Again, when you see log, you can simply just write a 10 at the bottom just so that you can remember what the base is. At some point you will always remember. And again, follow the arrows. 10 to the power of 2 is equal to 100, and so on. So whenever you get a logarithmic notation and you're still a bit confused about what it actually means in exponent notation, just remember the trick to follow the arrows. Now let's talk about the bases that we can use when we're using logarithms. Now, although technically we can take the power of a negative number, when it comes to using logarithms, we only use positive bases. So if we take this general expression and dissect it a bit, then what we just said is that this a should always be positive. Now let's ask ourselves this question. Again, let's do the trick of following the arrow. So a to the power of b is equal to x. Now, there are no restrictions on what b can be. B can be positive, it can be negative, it can be fractional, it can be whatever we want it to be. But what are we doing here? We're taking a positive number and we are putting whatever power that we want on it. Now, we can get super big values or super small values, but what we will never get is negative values, because a positive number to the power of anything will always be bigger than 0. And that is because we're starting with a positive base. So that means that the domain of the logarithm operation, the domain meaning what we are allowed to put in the logarithm, is only positive numbers. Now, before we get into the laws of logarithms, which as you will see are simply the other side of the coin of the laws of exponents, which we stated earlier, let me tell you about some special notation. Now, as we said earlier, when we say log, so simply log without any number here, that just simply means log base 10. So it's not really wrong to write the number 10 here at a base. It's just that by convention, when we write log, we directly mean log base 10. Now, another base that gets its own special notation is base e. So when you say ln of a, that simply means log base e. If you still haven't come across e, e is just simply a number. It's a special number, just like pi, and it's approximately equal to 2.7182 ... So it's an irrational number, which means the decimal places go on forever without any pattern at all. Now, for those of you who want to learn more about the number e, I will actually make a special video dedicated to that, talking about why this number is so special, how was it computed, and why is it very useful in mathematics. Now, as promised, we're going to get into the laws of logarithms. But before we do that, I want you to grasp the concept of logarithm even more. And so to make it even more clear in your head what logarithms actually mean, I will use base 10 because that's the base we're most familiar with, it's the base that we count with. Now, to do that, I will refer to the concept of scientific notation. And that is basically the idea of expressing any number in the form a times 10 to the power of b, where a is a number bigger than 0 and strictly less than 10. So for example, if we take the number 17 and we want to write it in the scientific notation, that would be 1.7 times 10 to the power of 1. If we take the number 29, for example, that is 2.9 times 10 to the power of 1. The number 301 is 3.01 times 10 to the power of 2. Now, if you take a smaller number, let's say 0.08, so to express this, we're going to have negative powers of 10 because this number is less than 1. So we're going to get 8 times 10 to the power of minus 2. I'm going to assume that this is something you're familiar with. If you're not, drop me a comment and I can for sure do a separate video covering how to write this notation, which is also part of the IB curriculum. In fact, it's actually mentioned in SL 1.1, which is the first ever concept that you're responsible for. So let's say 9,287. So that will be 9.287 times 10 to the power of 3. So the reason why this scientific notation is very useful is that it allows us to see how big this number is in terms of powers of 10. So 17 is of order 10 to the power of 1. Now 301 is of order 10 to the power of 2. So this notation allows us to look at the number in terms of how big is it in terms of powers of 10. Now this concept relates directly to logarithms. So if you have your calculator, I invite you to compute what is log of 17. And remember, log written on its own like that just means log base 10. Now log of 17 is approximately equal to 1.23. Now if you compute log of 29, you will find that it's approximately equal to 1.46. Log of 301 is approximately equal to 2.48. Log of 0.08 is approximately equal to minus 1.1. And finally, log of 9,287 is approximately equal to 3.97. Now, I want you to look at the numbers that have positive powers of 10. So 17 was of order 10 to the power of 1. Now, look at the log of 17. It's equal to 1.23. 29 is also of order 10 to the power of 1. And the log of 19 is 1.46. 301 is of order 10 to the power of 2. And the logarithm base 10 is 2.48. Now let's leave the negative power for now. We'll get back to it later. Let's finally look at the last number. So it's 10 to the power of 3, and the logarithm is 3 point something. So basically, when we say what is the logarithm of 17, we're saying how can we express 17 as a power of 10? So 17 is actually approximately equal to 10 to the power of 1.23. So in the scientific notation, that means that we just have one whole 10 and then a little extra bit that isn't a whole 10, which is this 1.7. Similarly, 29 is actually 10 to the power of 1.46. So we have one whole 10, which is pretty clear in the scientific notation, and then a little extra bit, which is this 2.9. 301 is the same thing. It's of order 10 to the power of 2. So the logarithm base 10 of 301 is 2 point something. And that little something corresponds to the 3.01. So if we take 10 to the power of 0.48, we will approximately get whatever is left here, which is 3.01. Now let's look at the last number, 9,287. So this number is of order 10 to the power of 3. However, 9.28 is also very close to 10. And so this becomes clear in the logarithm. The logarithm is approximately equal to 3.9, which can be rounded up to 4. So this is saying that 9,287 is approximately of order 10 to the power of 4. Now let's look at 0.08. Now for negative powers, it actually works the exact same way. Except here, it's not minus 2. Now the reason is this. So what we're saying is 0.08 is 8 times 10 to the power of minus 2, which means it's actually bigger than 10 to the power of minus 2. And obviously with negative powers, the bigger the absolute value of the number is, the smaller the value we get. So for example, 10 to the power of minus 3 is smaller than 10 to the power of minus 2. And so here, because 0.08 is actually bigger than 10 to the power of minus 2, in fact, it's 8 times more than that, so the logarithm base 10 is going to be more than minus 2. In fact, since 8 is almost equal to 10, you can actually round up 0.08 to 0.1, which means it would be 10 to the power of minus 1. And that is why here we have the logarithm equal to minus 1.1. So exactly same as the above, we start with minus 2 and we add a little extra bit, which corresponds to the extra value that we have here. And so minus 2 plus an extra bit, and that gives us minus 1.1. I hope looking at the scientific notation clarified even more the concept of logarithm and what is it that we mean by a logarithm. Now let's look at an example here. So we have log base 2 of x is equal to 3. So one way of doing it is to convert it to an exponent notation. So again, start from the base, we have 2 to the power of 3 is equal to x, and you've got your solution. So x is equal to 8. Now, what if our unknown was what we had on the right-hand side? So again, you can follow the arrows. 3 to the power of what gives us 9? So you can even write it in exponent notation. 3 to the power of x is equal to 9. And now it becomes obvious that x has to be equal to 2. Now, what about logarithm base 9 of 3 is equal to x? So again, what are we saying here? We're saying 9 to the power of something, our unknown, x, is equal to 3. And you should know that 3 is equal to the square root of 9, which means 9 to the power of a half. And that means that x here has to be equal to a half. Now, what is log base 2 of 16? So what are we saying here? 2 to the power of what gives us 16? And you should know that this is equal to 4. Now, what about log base 3 of x is equal to 3? So again, what are we saying here? We're saying that 3 to the power of 3 is equal to x. And that means that our x is equal to 27. So again, let's pause for a bit and think of what that means. So what we're saying here is that the logarithm of x base 3 is equal to 3. So this x here, how big is it in terms of powers of 3? Well, it's 3 to the power of 3. And that means that x has to be 27. Now, what if I ask you, what is the log base 6 of 1? So again, what are we asking here? We're saying, what is the power of 6 that will give us 1? So 6 to the power of x is equal to 1. Now, if we go back to the rules of exponents, you will see that this is the third rule that we wrote, that to get 1, any number can be raised to a power 0. And so that means that x has to be equal to 0 because 6 to the power of 0 is equal to 1. In fact, this is going to be true for any base. Log base a, so that's in general, of 1 is always equal to 0. And that is one of the rules that we will explicitly write later on. So the logarithm of 1 is equal to 0. Earlier on, I said that exponents and logarithms are inverse operations. So what does that actually mean? So let's look at an example. Log base 2 of 8. So by now, you should know that this is equal to 3. Again, if you're still unsure, follow the arrows. 2 to the power of what gives us 8, and the answer is 3. All right, now what if I say, what is 2 to the power of log base 2 of 8? So let's substitute. So log base 2 of 8, we just said is equal to 3. So that is 2 to the power of 3, and that gives us 8. So if you're observant here, you will see that what we got is exactly what we have here. So it kind of seems like this 2 and this log base 2 kind of canceled each other out, which is exactly what happened. Let's try with another example. So log base 3 of 9 is equal to 2. Now what is 3 to the power of log base 3 of 9? Again, we know log base 3 of 9 is equal to 2, so that is 3 to the power of 2, which gives us 9. And so again, the 3 and the log base 3 cancel and we're left with the 9. Now why is that happening? Well, if you understand what we mean by logarithm, this shouldn't surprise you at all. So what does log base 3 of 9 mean? It gives us the power that if we put on 3, we get 9. Or in other words, this is how big 9 is as a power of 3. So log base 3 of 9 is the power that if we put on 3, we get 9. And so we're taking that power and we're putting it on 3. And so obviously we end up getting 9. And so this is what I meant by the exponents and the logarithms being inverse operations. They actually cancel each other out when they come one after the other. Similarly, if the order switches, so if we have log base 2 of 2 to the power of 4, so again, what are we saying here? Follow the arrows. 2 to the power of what gives you 2 to the power of 4? It's a bit redundant, isn't it? It's just 4. And so again, what happened here? The log base 2 and the power of 2 seem to have cancelled. We're only left with the 4 here. Log base 5 of 5 to the power of 3. 5 to the power of what is equal to 5 to the power of 3? That is just equal to 3. So again, the log base 5 and the 5 cancel and we're only left with the power. So when we say that these two operations are inverses, that means that log base a of a to the power of x is going to give us x, and also a to the power of log base a of x is also going to give us x. It means they cancel one another, of course, given that they both have the same base. Now you will see why these two properties are very useful when it comes to solving equations, especially when our unknown is actually at the exponent. And this we will look at in more details when we look at IB type examples. Here we are being asked to evaluate the following. Log base 2 of square root of 2. So as you will see in all of these three examples, whatever we have inside the logarithm can actually be expressed as a power of the base. And that means we can actually compute these numbers without the use of any calculator. Obviously, this is not always the case. We could have a number here that cannot be expressed directly as a power of the base, and so you would need your calculator for it. But for now, let's look at this example here. So square root of 2, we know that this is equivalent to 2 to the power of a half. So we can rewrite it like this, and now the answer becomes obvious. What is the log base 2 of 2 to the power of a half? Or in other words, what is the power of 2 to the power of a half? And the answer is obvious, is equal to a half. Again, if you're unsure, do the trick of following the arrows. Start from the base, draw your arrows, and check 2 to the power of a half is equal to 2 to the power of a half. Next up, we have log base 5 of 25 square root of 5. Again, both 25 and square root of 5 can be written as powers of 5. So let's write it that way. So 25 is 5 squared times square root of 5 is 5 to the power of a half. And obviously here we could use the rules of adding the powers. So here we have log base 5 of 5 to the power of 2 plus a half, and that is equal to 5 over 2. And again, the answer becomes simple. What is the log base 5 of 5 to the power of 5 over 2? Again, you can kind of read this as what is the power of 5 to the power of 5 over 2. So obviously that is just 5 over 2. And again, if you follow the arrows, 5 to the power of 5 over 2 gives us what we have here. Now finally, log base 3 of cubic root of 9. Again, 9 can be expressed as a power of 3. 9 is simply just 3 squared. So let's just write this as 3 squared. And now the cubic root is the same as a power of a third. So we can substitute that. So this is 3 squared, all to the power of a third. And finally, we can use the law of multiplying the powers. So log base 3 of 3 to the power of 2 over 3. And again, the answer is simple here. It's 2 over 3. Now, I invite you to pause the video and try on your own to evaluate these 5 expressions. Again, in these examples, everything that you have inside the logarithm can actually be expressed as a power of your base, which, as we saw in the previous exercises, makes life so much easier. So let's start with the first one. So 1 over 9, let's start step by step. So 9 is 3 squared, so we can rewrite this as 1 over 3 squared. And now if we want to put the 3 at the numerator, all we got to do is just change the sign of the power. So we get 3 to the power of minus 2. And now the answer is simply minus 2. The second one is pretty obvious. So 1,000 is 10 to the power of 3, and so the answer is 3. Log base x of x squared. So here we don't even know what the base is, but again, the answer is obvious. X to the power of 2 is equal to x squared. What is this asking? It's saying how big is x squared as powers of x? It's as big as a power 2. Now the next one requires a bit of reflection here. So we know that 2 to the power of a half is equal to square root of 2, but now we're asking it the other way around. We're saying square root of 2 to the power of what gives us 2? If you simply follow the arrows, square root of 2 to the power of what gives you 2, then the answer becomes obvious. We just need to square root of 2 to get 2. Or another way, if you want to rewrite the 2 as a power of square root of 2, then you can simply say, okay, 2 is square root of 2 to the power of what? And again, the answer is obvious. It's to the power of 2. The square root and the power of 2 cancel and you get 2 back. And so the answer is 2. Now let's look at the last example here. Log base 25 of 5 is equal to. So again, you can follow the arrows. You can say 25 to the power of what gives me 5. And obviously you should know that the square root of 25 gives 5, which is a power of a half. Or you can express 5 as a power of 25. So you can say that this is log base 25 of the square root of 25. And again, the square root of 25 is nothing but to the power of a half, so the answer is obviously a half. Now let's look at a different type of exercises. So here we're not asked to simplify or evaluate. Here we're asked to solve an equation. So we have an unknown x, and we're supposed to find the value of x. So here the trick that I showed you about following the arrows comes in very handy. So if we say that log base x of 9 is equal to minus 3 over 2, that is equivalent to saying that x to the power of minus 3 over 2 is equal to 9. So in this way, we have gotten rid of the logarithms altogether, which, as you will see later on, is always our goal when it comes to solving equations that have logarithms. We want to get rid of the logarithms and end up with a simpler equation for x. So here, x to the power of minus 3 over 2 is equal to 9, and we're after x. So we need to raise both sides to a power such that we end up with a power of 1 here. Now, if you don't know this, to go from the power minus 3 over 2 to the power of 1, all we got to do is take the whole thing to the power of minus 2 over 3. And the reason that works is that when you multiply, the 2 and the 2 cancel out, the 3 and the 3 cancel out, the minus and a minus turn to a plus, and so we end up with x to the power of 1, which is what we want. And obviously, since this is an equation, we have to do the same on the other side. And so we get that x is equal to 9 to the power of minus 2 over 3. Now let's look at the second example, exactly same thing. So log base 5x of 125 is equal to 2. Let's follow the arrows. So that means that 5x to the power of 2 is equal to 125. Don't forget to put the brackets here because the power of 2 applies to both 5 and the x. And so we get 5 squared times x squared is equal to 125, and that means that x squared is equal to 125 divided by 25, and that is equal to 5. And that simply means that x is equal to square root of 5. And now it's time to actually dive deeper and look at the laws of logarithms and how we manipulate them within an algebraic expression.